All right, so welcome to Galvanic Cells number 3, and this is again going to be another practice problem, but what's going to be different about this one is it's also going to be based on the same principles of single replacement reactions, except for this one's going to include an acid as one of the cells, one of the half cells. And so it's going to be a little bit different setup. Before I go over that, I just want to remind you that not all galvanic cells are going to be based on these simple single replacement reactions. Some are more complex, and we'll practice those as AP problems. The only ones that you'll sort of have to be able to predict completely from scratch are these ones based on those types of single replacement reactions, like the ones we've done in the example problem so far. So let's set this up. All right, so in this case, we have two cells here. We have magnesium with magnesium chloride, and we have platinum with, this is an HCl. So this is obviously an acid. Well, what's kind of weird about this, and an example we haven't seen so far, is platinum is not the same thing as hydrogen. So we don't have both the metal and the metal ion here. And the reason why is because there is no solid form of hydrogen. So you've got to put some other electrode in. Now, why are we using platinum? Because that's very expensive. The reason why you have to use platinum is if you put most metals into acid, they'll do a single replacement reaction. So you have to put in a metal that won't corrode, that won't react with that. So that's going to be gold or silver or platinum or copper. So they tend to be precious metals that will get put in. You can also use graphite over time. That will wear down, but you will sometimes see that. So graphite, it would be carbon. So the nice thing about when you're working with acids is you know what's getting reduced, because there's no way to have an oxidation reaction on this side, because the platinum is just there to serve as an electrode. It's not there to be part of the reaction. It's just there to carry the charge, to act as a conduit for the electrons to move through. So what that basically means is if we know that this has to be reduction, it has to be, because that's all that can happen, we know what gets oxidized and what gets reduced. So you don't have to try two out. So if we come over to here, what gets oxidized? So if this is getting reduced, the magnesium has to get oxidized, which means we're starting with the metal and we're transitioning it into Mg2 plus 2 electrons. And this is going to be 2.37. On the table, it's negative 2.37, but we're flipping it over since it's oxidation. And reduction, remember when we write this one, just like with single replacement reactions, you have to make it 2H plus 2 electrons. And this is going to form hydrogen gas, just like in a single replacement reaction. I'm not writing very good H's today. Okay, and this is 0. So when we add the two of these together, we get 2.37 volts, and that's our E cell value. And that's how much voltage we'll produce if everything is at 1 molar, 25 degrees C, and 1 atm of pressure. And let's go ahead and add these up. There's 2 electrons here and 2 electrons here, so we don't need to multiply through by anything. We can just write our net ionic equation, and I'm going to change colors here. So we end up getting magnesium plus 2H plus gives us Mg2 plus H2. So again, it's really similar to a single replacement reaction. The only difference is it's going to happen in 2 separate containers connected to one another instead of it all happening in just one beaker. So I'm going to clear some space so we can draw our setups. Okay, so I've just transferred everything over, and I started drawing some of the setup just to save some time. So now when we look at the setup, we've got the magnesium ions and the magnesium electrode on this side, and we have the platinum and then the acid on this side, right? So H plus is always going to be acid. And we've got our salt bridge and then our wire connecting the 2 electrodes. So let's figure out what our anode and our cathode is. So magnesium is going to magnesium 2 plus. So that's going to be, it's losing 2 electrons. So this is where oxidation takes place. And that's going to be our anode. Oxidation always takes place at the anode. And the cathode, and remember, it doesn't matter which side is which, whichever one works. And so this is going to be our reduction. And that's our cathode. And this is getting reduced because it's picking up electrons. All right, so I want to come over to here. So what's happening is our magnesium is losing electrons and turning into magnesium 2+. So let's show that here with some arrows. So the magnesium electrode is going to, Mg is going to decrease in mass, and Mg2+ solution is going to increase in molarity because you're making more of the solution. All right, and if we come over to the other side, so what you have to be careful of here is this hydrogen is coming and this hydrogen ion is coming up. It's picking up electrons here, but it's not turning into more platinum. That doesn't really make any sense. Hydrogen can't turn into platinum. So instead, the platinum is just a place where the electrons are getting picked up. And so this is creating hydrogen gas, right? Because that's what the reaction tells us. If you get confused and you're not sure what's going on, always come back to the reaction because that tells you what the whole story is. So we're producing hydrogen gas. And so in this case, nothing is going to increase in mass. So we're producing, I guess you could say the volume. I mean, the mass of H2 is increasing. It's being created. We don't really measure that. So we're producing hydrogen gas, and nothing is really happening to the electrode itself. And it's decreasing in molarity for the H+ because it is getting used up. Okay, so let's come over and label the salt bridge. So for the salt bridge, the Na is moving, because that's your cation, it's moving towards the cathode to replace the H+ that's getting lost, because that's decreasing. And the Cl-, which is the anion, moves towards the anode. That would be helping to balance out the extra Mg2+, which is created. And then our last step is to come back over and to show the transfer of electrons. So in this case, the electrons are going from the anode. So these arrows are the electrons. Transfer of electrons. Okay, and if this is exactly 1 molar each, this will produce 2.37. So obviously, as this goes on and the molarity of this decreases and the molarity of this increases, right, your voltage will drop. So over time, the voltage will drop because you'll have less of this. And remember, this is your reactant, right? Reactant will decrease over time, the molarity, right? And over here, your product molarity is increasing. So over time, what that's going to do, what this here and this here is going to do, that's going to decrease your voltage. Now, if I wanted to make a battery, though, that had an increased voltage, I'm going to back this up for a second here just so we can kind of have some extra space. That's fine there. So let's say I needed to make a battery and I needed it to be at least 4 volts. So I'm making a battery and I need to produce 4 volts in order to power some sort of light. So if I need this to be at a certain voltage, I can play around with my molarities, and that will allow me to create something that has a specific voltage. So just change colors here. So something that would allow me to increase my voltage might be to increase my concentration. So I'm going to make this 2 molar or 6 molar, 8 molar, however much molar I want of my H+, right? So that's going to be my HCl. It's going to make the acid more concentrated. And let's say I'm going to drop this all the way down to 0.1 molar for the magnesium 2+. So in this case, H+ is my reactant, right? That's where it is. So this is my reactant. And this one is my product. And again, I'm only worried about what's in solution because the solids don't affect the voltage. So in this case, I have more reactant. And anytime I have more reactant than I have product in terms of molarity, that will create an increased voltage. And if I did vice versa and I flip this around, that would create a decreased voltage because I'd have more product than reactant. So if I switch this and I made this here, so just so we see both examples. Now if I decrease both to, let's say, 0.1 molar, then again the voltage will go back to 2.3 because the ratio, you're looking at the ratio. So if we look at this, let's say we have 2 molar of Mg, 2 plus, and we have 0.5 molar, really doesn't matter which numbers you picked, of H plus. This is my product. This is my reactant. And anytime I have more product than reactant, that's going to decrease the voltage. Okay, so it'll be something below 2.37. So that's the end of the tutorials. This should give you enough examples. We will practice several AP examples in class. They're a little too hard to draw out here with more complex reactions, and we'll practice several of those. But this should at least give you started on the concepts and the background behind it, and the more that you practice these, the better you'll get at them.